Hey everyone, and welcome to This Explainer. We're going to demystify exactly what happens inside the database engine during those hidden, split-second moments right after you hit execute. You type your query, send it off, and boom, results appear. But what is the actual journey your data takes behind the scenes? So, let's unpack this mystery for a second. Your SQL query is, at its core, just plain English text, right? It's literally just a string of characters. So how in the world does the database magically understand it, process it, and find the absolute fastest way to pull your data out of gigabytes or even terabytes of massive storage?
Well, to answer that, we've got to follow the exact chronological pipeline that every single query takes. It goes through these 5 distinct execution stages before a single piece of data is ever even touched. It's basically a highly intricate assembly line of logic.
All right, kicking things off with stage 1, parsing. This is where the database essentially acts like a super strict grammar checker. It reads your raw SQL text, makes sure your syntax is perfectly correct, and then it draws out the structure on this diagram called an abstract syntax tree. It's mapping out the subjects, the verbs, and the objects of your command before anyone even tries to figure out what it actually means.
Next up, semantic analysis takes over in stage 2, which we call binding. Think of this stage like a fact checker reviewing a totally grammatically correct sentence, like the purple elephant flew to the moon. I mean, the grammar is fine, but the facts absolutely do not check out. So here, the database is making sure that tables and columns you asked for actually exist in the schema, and super importantly, that you actually have the proper permissions to view them.
Okay, now we reach the absolute climax of the journey and the real brains of the whole operation, the query optimizer. Did you know a single SQL query can have thousands of equivalent execution plans, all with wildly different performance outcomes? The optimizer's entire job is to generate those plans, estimate how much they'll cost to run, and pick the absolute cheapest one.
And honestly, the optimizer is exactly like the GPS on your phone calculating a route based on live traffic, not just distance. It tests thousands of possible execution plans to find the actual fastest route to your data. Because, let's be real, the shortest path on a map is completely useless if you're stuck in bumper-to-bumper traffic.
So, the most fundamental decision this GPS has to make is choosing between an index scan and a full table scan. A lot of us just naturally assume that an index is the ultimate speed hack, right? But, counterintuitively, using an index is not always the fastest route.
The winner of that whole debate relies entirely on one magic word: selectivity. Selectivity is just the fraction of rows that match your query's condition. If, say, 90% of the rows match what you're looking for, reading the whole table sequentially is actually way faster. But if only 0.1% match, then the index wins decisively. No contest. To put that into perspective, imagine trying to find a really rare word using the index at the back of a physical book. You flip to the back, find the page number, and boom, you go straight to it. Perfect. But now, compare that to using that exact same index to find every single occurrence of the word the. Flipping to the index, then jumping to 10,000 different pages, that would take so much longer than just sitting down and reading every page sequentially. And that is exactly how your database thinks. All right, let's translate some of this jargon and look inside the explain command. This is an awesome tool that exposes the exact route the optimizer chose to execute your query, basically letting us peek right inside its brain. When you actually run explain, you're going to see 4 specific scan types that tell you exactly how the execution engine is fetching your rows from the physical disk. A sequential scan means it's reading every single page. An index scan means it's following a B tree. An index-only scan is the absolute best because all your data is right there in the index. It doesn't even need to touch the main table. And finally, a bitmap heap scan collects all the index locations first and then reads the pages physically to minimize random disk reading. Looking at that explain output, you're also going to spot the estimated cost, which is kind of the optimizer's own made-up expense metric, and the estimated row count. Now listen up, because here is a massive red flag. If the estimated rows wildly differ from the actual rows processed, it means your table statistics are stale. Your optimizer is essentially driving blind because it's working with outdated maps.
Okay, moving on. Now that we know how a single table is scanned, let's demystify joins and unravel how databases internally merge 2 tables together.
The first method here is the nested loop join, which scans table B for every single row in table A. Think of this like checking a 30-person class list against a giant school attendance sheet. You take one name, scan the whole sheet, and repeat. It's totally fine for small datasets, but it is literally terrible for massive ones, unless, of course, the inner table has an index to speed up those lookups.
Now, if you have really large tables and zero indexes, the database gets pretty clever and uses what's called a hash join. It builds an in-memory directory from the smaller table, so it can instantly look up rows from the larger one. It's kind of like building a quick phone directory in your head for instant lookups, instead of scanning the entire phone book every single time.
And finally, we have the merge join. This method elegantly zips two tables together at the exact same time. It's just like merging two already sorted decks of cards by simply comparing the top card of each deck. It is incredibly fast, but the catch is it requires both tables to already be sorted or indexed on the join column. What's really fascinating here is how these algorithms perfectly balance performance trade-offs based on your memory and what indexes you have available. Look at how a nested loop uses really low memory but leans heavily on indexes, while a hash join eats up high memory but doesn't need an index at all. The optimizer is just back there balancing all these variables perfectly for you. Okay, so once the optimizer finally locks in its scan and join strategies, it hands the master plan over to stage 4, the execution engine. The engine physically pulls the pages from the disk, assembles the final rows, and then delivers stage 5, the result. And it ships it right back to your application in a matter of milliseconds.
Let's wrap this up with some SQL superpowers and practical takeaways. Because understanding this invisible journey isn't just cool theory, it directly gives you the power to write significantly faster SQL. Here's what you can start doing today. Before you ever guess why a query is slow, just run explain. Break the habit of writing select star. It literally chokes the database with unnecessary data and blocks those blazing fast index-only scans. Remember the golden rule. Indexes speed up your reads, but they physically penalize your writes. Trust the optimizer to handle your join order, and please run analyze to fix stale statistics so your database isn't flying blind.
So take a hard look at your own database today and ask yourself a really tough question. Are your indexes actually helping you, or are they just needlessly slowing down your database writes? Do your query plans reflect reality, or are you long overdue for an optimization overhaul? Keep exploring these invisible journeys, apply what you've learned, and we'll catch you in the next explainer.